Hi everyone. So today you're going to learn about chemical bonding. So there are three different types of chemical bonds, but we're only going to cover two of them. And you're also going to learn the different types of compounds and how to name them. So I want to start off the lesson by showing you some images here. So the first one on the top left corner is a geode. And a geode is basically a spherical rock containing a hollow cavity with crystals growing inside. So these crystals are basically a type of compound. Okay, so it contains calcites and compounds containing carbonates. This one on the right hand side is a cavern. So it's a cave that's 700 feet below the ground and it's in New Mexico. It's called Carlsbad Caverns. So if you've been there, the caves contain really interesting structures made of calcites, made of limestone, right? So you have these stalagmites and stalactites that are basically made up of compounds, ionic compounds. And the one here at the bottom is a limestone. It's a mountain made of limestone. So you have so limestone is basically a type of ionic compound that's similar in composition as these other two here, geode and stalagmites and stalactites. So it's that one thing that they have in common is that a lot of them are made up of calcium carbonate, which is basically an example of an ionic compound. It's an ionic compound because it's composed of ions like cations and anions. So this white powder that's shown here is not sugar, and it's not cocaine either. But it kind of looks like cocaine, and you don't have to be a chemist or a user in order to know what cocaine looks like. But I can assure you this compound here is actually calcium carbonate. This white powder is calcium carbonate. So that's the name of the compound, calcium carbonate. The one underneath it is the chemical formula of that compound, calcium carbonate. Okay? And this compound is a perfect example of what they call ionic compound, because ionic compounds contain ions, as I mentioned earlier. So you have positively charged cations and negatively charged anions. So the calcium here contains that positive charge, whereas the carbonate ion is your anion containing the negative charge. So let's look at ionic compounds in a little more detail. So you learned in the previous chapters what a compound is. A compound is basically a pure substance, right? There are two types of pure substances. There's elements and there's compounds. Compounds are a substance containing multiple different elements that are stuck together via chemical bonds. So that's the definition of a compound. It's a bunch of elements joined together by chemical bonds. Now, these chemical bonds involve valence electrons. And if you remember from the previous lesson, that valence electrons are the ones that are at the outermost layer of an atom or an element, right? They have high energy. And so these are the electrons that are involved in chemical bonding, in chemical reactions. Okay, so chemical reactions involve breaking bonds and formation of bonds. And so ionic basically means that it contains ions. So you can have cations and anions, or positive versus negative charge. So an ionic compound contains cations and anions that are bonded together via chemical bond. And here are some examples of cations. You can have metals. So all metals, they have positive charge. Okay, because metals tend to lose electrons. And so when a metal loses an electron, it forms a positive charge. And anions, on the other hand, are a bunch of non-metals, okay, like chlorine, nitrogen, fluorine, and so on and so forth. And these non-metals, they tend to gain electrons. And so when they get an additional electron, they form a negative charge. So for example, here the chlorine has a negative charge. So that tells you that this chlorine, a chlorine atom gained an additional electron giving it a negative charge. And this structure or formula here, CO3, with a negative 2 charge, tells you that it contains 2 additional electrons because electrons are negatively charged. Now let's look at valence electrons in terms of bonding. To visualize bonding, elements are represented by what they call Lewis dot symbols. So a Lewis dot symbol is basically the symbol of the element, like for example hydrogen, and then it's surrounded by dots. And that's why they call it Lewis dot symbols. It's a symbol of the element followed by dots. And these dots are represented, these dots basically represent the number of valence electrons for that specific element. So let's look at some examples here. So again, Lewis dot symbols are basically symbols of the element surrounded by dots, and the dots are valence electrons. So for example, let's look at these 8 elements right here. So you have lithium, which is group 1, you have beryllium, group 2, all the way to group 8, which is neon, right? It's a noble gas. Lithium, well, let's go back a little bit here and look at how we can determine the number of valence electrons per given element. So if you remember from the previous chapter, the number of valence electrons basically matches the group number. So that's true for the main group metals. And you don't have to worry about transition metals, the metals that are in the middle of the periodic table. We only care about the main group metals. So the number of valence electrons matches the element's group number. So lithium is in group 1, right? Group 1A. So that tells you that lithium contains 1 single valence electron. Okay, so it's got 1 electron in its outermost shell or outermost subshell. And so when you draw the Lewis dot symbol, all you have to do is put a single dot right next to the symbol, lithium. So this right here is the Lewis dot symbol for lithium. We can do the same thing for beryllium. Beryllium is in group 2, so it's got 2 valence electrons, and you would put it around beryllium. So it doesn't matter, you can put a single electron here or a single electron here on the left, right? So this is the Lewis dot symbol for the element beryllium because beryllium contains 2 valence electrons. So boron is group 3, you would have 3 valence electrons. Carbon is in group 4, 4 valence electrons. Nitrogen 5, oxygen 6, fluorine 7, and neon is in group 8, so it has 8 valence electrons. So this is how you write the Lewis dot symbols for elements in the periodic table. So let's look at the classifications of some of these elements really quickly. You remember that lithium is a type of alkali metal, and beryllium is an alkaline earth metal. And then you have the group 7 elements, which are called halogens, and then the group 8 elements, which are called noble gases. And so you also learned in the previous chapters the physical and chemical properties of these groups of elements, right? In chapter 2, I believe, or one of the previous chapters, you learned that Mendeleev and Moseley basically arranged the elements in the periodic table so that the elements with the same physical and chemical properties would fall in the same column or same group. And so the alkali metals are the most reactive metals in the periodic table. Okay, alkaline earth metals are semi-reactive, whereas the halogens are the most reactive non-metals. And the noble gases are the most stable elements in the periodic table because they are unreactive. So they are happy with the number of electrons that they have. And so atoms or ions are stabilized when they are isoelectronic with a noble gas. So if you remember the term isoelectronic, it means the same number of electrons. In other words, the same electronic configuration. Okay, so a lot of metals and nonmetals, they tend to gain or lose electrons so that they become isoelectronic with a noble gas. And so when they have the same number of electrons as a noble gas, then they are considered stable, because noble gases are themselves stable and unreactive. So when an atom or an ion has a total of 8 valence electrons, that means that they're following the octet rule, is what they call them. So if you have 8 valence electrons total, that means that you're satisfying the octet rule, which is basically the rule of 8 valence electrons. And when you have 8 valence electrons, then that atom or ion is considered stable. So looking at the first 3 elements here, which are the metals tend to lose electrons. All right, so you learned that in previous chapters, that metals tend to lose electrons in order to achieve an octet. But instead of using this phrase here, achieve an octet, we're going to use isoelectronic with a noble gas. That would be the more proper phrase here. So metals tend to lose electrons in order for them to become isoelectronic with a noble gas. And so when an atom or ion is an isoelectronic with a noble gas, that means they become stable. They are stabilized. So here are a few examples. We have lithium ion, beryllium ion, and aluminum ion. So as you can see, you can always try to calculate the total number of electrons that a lithium ion has. So lithium is the 3rd element in the periodic table, and so it has 3 electrons. With a positive charge, that tells you that you subtracted 1 electron, and so 3 minus 1 equals 2 electrons left. So lithium, beryllium, and aluminum, these 3 ions are isoelectronic with each other, meaning they all have only 2 electrons. And because they contain 2 electrons, they are isoelectronic with the noble gas helium, because helium is a noble gas with atomic number 2, so it's got 2 electrons. So that makes these 3 ions stable. They become as stable as a helium atom. Looking at these other elements here, we have the nonmetals, and the nonmetals tend to gain electrons in order to achieve an octet or become isoelectronic with a noble gas. So let's say nitride ion, oxide ion, and fluoride ion, you can see that they have negative charges, and these negative charge tells you that they have additional, or they have gained additional electrons. So nitrogen, for example, it has the atomic number 7, and so a negative 3. So that means that a nitrogen atom contains 7 electrons, and a nitrogen ion with a negative 3 charge contains 3 additional electrons. So 7 plus 3 gives you 10 electrons. Same thing for oxygen. Oxygen has atomic number 8, and you add 2 electrons to it, you get 10. Fluorine is 9, plus add 1, you get 10 electrons. And so all these ions shown here have a total of 10 electrons. And so they are isoelectronic with the noble gas neon, because neon has the atomic number 10 in the periodic table. And so these anions shown here are all stable. They are all stable as a neon atom. So the next concept that I want to cover here is the ionic charge. So this is the electrical charge of an ion. So regardless whether you have a cation and an anion, they have what they call ionic charge. So let's look at the first group here on the left, the group 1 elements. So group 1 elements tend to have a positive 1 charge. Like lithium, for example, lithium plus, sodium plus, K plus, and so on. And the reason why group 1 elements tend to have a plus 1 charge is because they lose 1 electron. They tend to lose 1 electron. And so if you remember, the number of valence electrons for a specific element is equal to the element's group number. And so group 1 elements contain 1 valence electron, and it's actually that single valence electron that they lose in chemical reactions. So when lithium loses its valence electron, it forms a positive charge. Same thing for the rest of the elements in group 1. Group 2 elements, on the other hand, contain 2 valence electrons. And so when these elements react, then they lose 2 valence electrons. And when they lose 2 electrons, then they become isoelectronic with a noble gas. And so group 1 elements, the alkali metals, tend to have a positive 1 charge. The group 2 elements, alkaline earth metals, tend to have a positive 2 charge because they've lost 2 valence electrons. And now you can kind of predict what group 3 elements would have, right? They would have a positive 3 charge because they would lose those 3 electrons, those 3 valence electrons. So group 3 elements would form a positive 3 charge. We're going to skip group 4 because that's special. But typically group 4 elements tend to form a positive 4 charge. Carbon is a special case. The element that's right below carbon is silicon, and silicon tend to have a positive 4 charge. Group 5 elements tend to have a negative 3 charge, and the reason why is because nonmetals, because now we're accessing the nonmetals here, they tend to gain electrons. And so when nitrogen gains 3 additional electrons, then it becomes isoelectronic with the next noble gas, which is neon. Okay? And so nitrogen, phosphorus, and the elements right below that will contain a negative 3 charge. Group 6 elements like oxygen and sulfur, they tend to have a negative 2 charge. Again, they tend to gain electrons in order to become isoelectronic with the next noble gas. Fluoride ion, negative 1, and then the group 8 elements tend to have 0 charge. They're neutral. These transition metals that are in the middle of the periodic table, can also have an ionic charge because they are metals. Metals tend to lose electrons, and so they gain a positive charge. But they're not as predictable compared to the main group elements. So that's one of the physical and chemical properties that are unpredictable for transition metals. And the reason why they're not as predictable is because of the fact that these transition metals can have multiple possible ionic charges. So for example, chromium can have a positive 3 charge. It can also have a positive 6. Iron can have a positive 2 charge or a positive 3. Manganese can have a positive 2. It can have a positive 4 or even positive 7. And so the ionic charge of these transition elements are not as predictable compared to the main group elements that we just looked at. Although there are some exceptions, some transition metals that have only one type of ionic charge. And so you should remember, I'm going to name 3 of them and you should remember them. The first one is zinc. So zinc always has a positive 2 charge. The second one is silver. Silver will always have a positive 1 charge. And the third one is scandium. Sc, scandium, number 21. It will always have a positive 3 charge. So these 3 metal ions or transition metals, zinc, silver, and scandium, have predictable ionic charges.